In the spring of 1900, Greek sponge divers were sailing home from North Africa. A storm forced them to take shelter near Antikythera, a small island between Crete and mainland Greece. While waiting out the weather, one diver descended to explore the sea floor. At 45 meters depth, he found something impossible. The shipwreck. The diver surfaced, reportedly claiming he'd seen dead bodies on the sea floor. His captain dove to investigate. What they'd found wasn't bodies. It was statues, bronze and marble sculptures scattered across the seabed. An ancient shipwreck, laden with treasures. The ship had sunk around 60 to 70 BC, roughly 2,000 years before the divers found it. The salvage. Greek authorities organized a salvage operation. Divers recovered bronze statues, marble sculptures, pottery, glassware, coins, jewelry, and one corroded, unrecognizable lump of bronze. Nobody paid much attention to it. It looked like scrap formless. Unimportant, it was cataloged. Stored, mostly forgotten. The discovery. Months later, the bronze lump split open. Inside, gears. Dozens of interlocking bronze gears. Inscriptions in ancient Greek. Mechanical components fused together by 2,000 years of corrosion. Someone had built a machine, a complex machine, and it had gone down with the ship. Archaeologists were baffled. Ancient Greeks didn't make machines like this. They made pottery, statues, architecture, not geared mechanisms. The initial confusion. Early researchers proposed theories. A navigational instrument, an astrolabe, some kind of clock, maybe even a fake, created in modern times and planted. None made sense. The gears were too complex for a simple astrolabe. The inscriptions referenced astronomical cycles. And the craftsmanship, even corroded, showed precision beyond what ancient technology should achieve. The X-ray revelation. In 1951, British physicist Derek de Solla Price began studying the mechanism using X-rays. What he found shocked the scientific community. Inside the corroded mass, at least 30 bronze gears, different gear ratios carefully calculated, inscriptions describing astronomical phenomena, pointers that once moved across dials, a front face showing zodiac and calendar, back faces showing lunar and eclipse cycles. This wasn't a simple instrument. This was an analog computer, built 2,100 years ago. The impossibility problem. Geared mechanisms of this complexity shouldn't exist until medieval Islamic astronomy, 1000 as AD. Renaissance European clockmaking, 1400s, 1500s AD. Industrial Revolution precision engineering, 1700s, 1800s AD. Yet here was a device from 100 BC that rivaled anything made before the 1800s. The Antikythera Mechanism was more than 1,000 years ahead of its time. How? The knowledge implication. If Greeks could build this, what else could they build? The mechanism suggests advanced mathematical knowledge, sophisticated astronomical theory, precision metalworking techniques, mechanical engineering understanding, manufacturing capability. None of which appears in surviving ancient texts. Either we've completely underestimated ancient capabilities, or massive amounts of knowledge were lost. Probably both. The Singleton problem. The Antikythera Mechanism is unique. No other examples have been found. No ancient texts describe how to build it. No similar devices exist in the archaeological record. It's a technological orphan, an artifact with no clear predecessors or successors. This suggests either it was an isolated genius creation, or many similar devices existed and we've only found one. Given that this one survived by accident, shipwreck preservation, the second option seems likely. How many other mechanisms corroded away? Melted down for scrap? Lost to time? The modern reconstruction. In the 2000s, researchers using modern imaging technology created detailed scans of the mechanism. They identified more gears than previously known, complex gear ratios matching astronomical cycles, inscriptions like an ancient user manual, evidence of sophisticated machining. Computer models showed the mechanism could predict positions of the sun and moon, track planetary motion, calculate lunar phases, possibly predict eclipses, display the timing of ancient Olympic games. This wasn't a simple calculator. This was a sophisticated astronomical computer. The question: how did an ancient Greek engineer, whose name we'll never know, create something that wouldn't be equaled for 1,500 years? What knowledge did they possess? And why did that knowledge disappear so completely that medieval scholars had no idea such devices had ever existed? The Antikythera mechanism contains at least 30 bronze gears. Each gear has between 15 and 223 teeth. The teeth are precisely cut, evenly spaced, designed to mesh smoothly with adjacent gears. The gear ratios correspond to astronomical cycles, lunar months, solar years, eclipse periods. This isn't random craftsmanship. This is precision engineering. The gear cutting problem. Bronze Age and Classical Greek metalworking typically produced weapons, armor, statues, decorative items, not precision gears. Cutting gear teeth requires consistent spacing, accurate angles, smooth surfaces for meshing, minimal friction. How did an ancient craftsman achieve this? The tools. Ancient Greeks had bronze and iron tools, files and chisels, measuring devices, calipers, rulers, lathes for turning metal. These are basic tools, not precision machine tools. Yet the Antikythera gears show teeth cut with remarkable uniformity, gear ratios calculated to match astronomical cycles, components that fit together with minimal play. Someone, somewhere, figured out how to manufacture precision gears using ancient tools. The mathematical knowledge. The gear ratios aren't arbitrary. Example: one gear train represents the Metonic cycle, the 19-year period after which lunar phases repeat on the same solar calendar dates. The mechanism uses gear ratios of 53.19 teeth, 223.19 teeth. Other ratios matching astronomical periods. Whoever designed this knew advanced mathematics, fractions, ratios, cycles, astronomical theory, eclipse prediction, planetary motion, mechanical engineering, how gears transfer motion. This is interdisciplinary expertise, not something a single craftsman could improvise. The differential gear. One of the mechanism's most sophisticated features. A differential gear. A differential allows two inputs to combine into a single output. In the Antikythera mechanism, it calculates the synodic month, the time between full moons, by combining the solar year cycle, the lunar month cycle. Differential gears weren't rediscovered until the 1500s, 1600s. Yet here's one from 100 BC, the inscriptions. The mechanism is covered in tiny Greek text. Over 3,000 characters have been identified, about 95% of the original text. The inscriptions are instructions for use, descriptions of astronomical phenomena, labels for dials and pointers, essentially an ancient user manual. This suggests the mechanism was not a one-off experiment, designed to be used by someone other than the maker, part of a broader tradition of such devices. The manufacturing process. Researchers have proposed construction methods. 1. Design phase. Calculate gear ratios for astronomical cycles. Design gear trains to produce correct outputs. Plan the layout of components. 2. Gear cutting. Cast bronze gear blanks. Mark tooth positions using dividers. Cut teeth with files and chisels. Smooth surfaces for meshing. 3. Assembly. Mount gears on axles. Align gears precisely. Enclose in wooden and bronze case. Add inscriptions. This is sophisticated manufacturing, not artisan improvisation. The workshop question. Where was this built? Possibilities. Rhodes, known center of astronomy and mechanics. Syracuse, Archimedes' home, center of mathematical innovation. Alexandria, Library of Alexandria, center of scholarship. Corinth, mentioned in inscriptions on the mechanism, we don't know for certain, but it required a workshop with skilled craftsmen, access to astronomical knowledge, funding, bronze wasn't cheap, intellectual tradition supporting such work. This wasn't made in isolation. It came from a sophisticated technological environment. The precision analysis. Modern studies using CT scans reveal gear teeth cut with accuracy of fractions of a millimeter, consistent tooth spacing across all gears, evidence of machining techniques, turning on a lathe, signs of where the device was actually used. The precision isn't perfect by modern standards, but it's remarkable for ancient technology, and it worked. The mechanism could calculate astronomical positions accurately enough for practical use. The quality control. Some gears show modifications. Teeth that were recut to improve meshing. Adjustments to improve accuracy. Evidence of trial and error refinement. This suggests the maker tested the mechanism, made corrections, refined the design through iteration. This is engineering methodology. Problem solving through testing and improvement. The lost tradition. The Antikythera mechanism isn't mentioned in any surviving ancient text. No how to build an astronomical computer manuals exist. No ancient scholars describe such devices either. The knowledge was considered proprietary, guild secrets, or texts describing it were lost, or such devices were common enough not to require special documentation. Given the sophistication, the first two options seem most likely. Knowledge was lost, texts disappeared, the tradition died. For decades, researchers debated what the Antikythera mechanism actually did. Early theories ranged from navigation tool to clock to orrery. Only modern technology, CT scans and 3D imaging, revealed its true purpose. It was an astronomical calculator, a computer for the cosmos. The front dial. The main front face displayed the zodiac calendar, Greek zodiac signs, the Egyptian calendar, 365-day solar years, a pointer showing the sun's position. Users could turn a crank on the side. As the crank turned, the sun pointer moved through the zodiac. The date advanced on the calendar. Other dials updated correspondingly. This showed the sun's position for any given date. The moon dial. A sub-dial on the front showed lunar phase, new moon, full moon, etc. Moon's position in the zodiac, calculated using the differential gear, the moon dial was remarkably accurate. It accounted for the moon's varying speed in its elliptical orbit, something requiring sophisticated astronomical knowledge. The upper back dial. The back of the mechanism had two large spiral dials. The upper one displayed the Metonic cycle, 19-year calendar cycle, subdivided into months, with lunar months marked. This allowed prediction of when lunar months would align with solar years. Useful for calendar coordination, religious festivals, many based on lunar-solar alignment, agricultural planning. The lower back dial. The lower back dial showed the Saros cycle, 18-year eclipse prediction cycle, subdivided into months, marking when eclipses would occur. This is extraordinary. Eclipse prediction requires understanding. Lunar orbital mechanics. Solar-lunar positional relationships. Geometric relationships between Earth, Moon, and Sun. Ancient Babylonians developed eclipse prediction methods. The Greeks refined them mathematically. The Antikythera mechanism automated the calculations. The planetary display. Some researchers believe the mechanism also showed planetary positions: Mercury, Venus, Mars, Jupiter, Saturn. Evidence. Inscriptions mentioning planets. Gear trains that might represent planetary cycles. Pointers on the front dial. This remains debated. Some gears are too damaged to reconstruct fully, but if it did track planets, that makes it even more sophisticated. The Olympic Games. One inscription mentions the Na Games, believed to be the Na Games, one of several Pan-Hellenic competitions like the Olympics. The mechanism possibly showed when games would occur based on calendar cycles, helping plan travel to events. This suggests practical, everyday use, not just academic interest. The operating procedure to use the mechanism. 1. Turn the crank to set the desired date. 2. Read the front dial to see sun and moon positions. 3. Check sub-dials for lunar phase and other data. 4. Read back dials to check for upcoming eclipses. 5. Use the information for calendar planning, navigation, celestial positioning, religious festivals, academic study. It was a portable reference device, an ancient almanac, a computer for anyone needing astronomical data. The accuracy. How accurate was it? Modern analysis suggests solar position, accurate within a few degrees. Lunar position, accurate within a degree. Eclipse prediction, reliable for predicting time windows. Not perfect, but functional for ancient needs. For comparison, better than manual calculations, faster, less error-prone. Not as accurate as modern computers, sufficient for navigation, calendar, and prediction. The knowledge requirement. To build this, the maker needed to know Greek astronomical theory, Babylonian mathematical methods, geometric models of celestial motion, observational data for cycles, mechanical engineering to implement calculations. This wasn't folk knowledge. This was cutting-edge science. The user base. Who would use such a device? Possibilities. Astronomers, academic study, navigators, celestial positioning, calendar keepers, religious and civic officials, wealthy patrons, intellectual prestige, teachers demonstrating celestial mechanics, the demonstration function. Some researchers propose the mechanism was also educational, demonstrating how the cosmos worked, showing celestial cycles visually, teaching astronomical theory through mechanical model like a planetarium. But pocket-sized, relatively, it was about the size of a shoebox. The lost function. We probably don't understand everything it did. Some gears are too damaged to reconstruct. Some inscriptions are illegible. Possibly it had additional functions we'll never recover. The device we see is incomplete. The device that sank with the ship may have been more complex still. The Antikythera Mechanism represents knowledge from multiple ancient traditions. It's not Greek in isolation, it's a synthesis. The Babylonian Foundation. Babylonian astronomers, around 700 to 300 BC, developed systematic observation of celestial phenomena, mathematical models of planetary motion, eclipse prediction cycles, Isaros cycle, lunar and solar period calculations. The Babylonians were obsessive record keepers. For centuries, they tracked moon phases, planetary positions, eclipse occurrences, seasonal changes. From this data, they extracted patterns, cycles. Predictive models. The Antikythera Mechanism uses Babylonian cycles, particularly the 223-month Saros eclipse cycle, the Greek contribution. Greek astronomers and mathematicians refined Babylonian observations. Hipparchus, 190–120 BC, calculated the length of the solar year, discovered the precession of the equinoxes, measured lunar cycles with precision, created star catalogs. Archimedes, 287–212 BC, built mechanical devices, described in texts but now lost, developed geometric models of celestial motion, possibly designed orreries, mechanical solar system models. The Greeks turned Babylonian observations into geometric models. They asked why, not just when. The mechanical tradition. The Greeks had a tradition of building mechanical devices. Ctesibius, 285–222 BC, invented the water clock, created pneumatic devices, pioneered mechanical automation. Philo of Byzantium, 280–220 BC, wrote treatises on mechanics, described automata and machines Archimedes. Again, ancient sources mention his sphere that showed planetary motion, possibly a mechanical device similar to the Antikythera Mechanism. This wasn't an isolated invention. It came from a tradition. The missing link. Here's the problem we have: Babylonian astronomical data, Greek mathematical theory, Greek mechanical engineering tradition, the Antikythera mechanism itself. But we don't have detailed treatises explaining how to build such mechanisms, other surviving examples of similar devices, clear documentation of the knowledge transfer. The knowledge clearly existed. The mechanism proves it, but the texts explaining it are gone. The Library of Alexandria. The Library of Alexandria, founded around 300 BC, was the ancient world's greatest repository of knowledge. It contained hundreds of thousands of scrolls, works from across the known world, scientific, mathematical, and engineering texts, copies of rare and unique documents. Scholars at Alexandria. Eratosthenes measured Earth's circumference, Euclid, geometry, Apollonius, conic sections, Hypatia, mathematics and astronomy. If there were texts explaining how to build astronomical mechanisms, they'd be in Alexandria. The Great Loss. The Library of Alexandria was destroyed. Not in a single fire, as popular myth claims, but gradually. Caesar's siege, 48 BC. Partial destruction. Later fires and neglect, continued loss, Christian period, 391 AD, destruction of pagan texts, Arab conquest, 641 AD, final dispersal by 1000 AD, essentially nothing remained. Hundreds of thousands of texts, gone. How many described devices like the Antikythera mechanism? How many explained astronomical calculations, gear ratios, mechanical designs? We'll never know. The knowledge cascade. When Alexandria declined, knowledge didn't just stay in one place, it scattered. Some texts preserved in Byzantium, some translated into Arabic, Islamic scholars, some copied by medieval monks, most lost entirely. What survived was incomplete, fragmentary, often mistranslated. Ancient scientific works were especially vulnerable. Religious authorities sometimes opposed pagan knowledge. Technical diagrams didn't copy well. Specialized terminology was misunderstood. Mechanical devices couldn't be preserved without understanding. The medieval ignorance. By the medieval period, 500 to 1400 AD, European scholars had lost most Greek scientific texts, no knowledge of sophisticated ancient mechanisms, limited understanding of astronomy, crude mechanical devices. When medieval engineers rediscovered geared mechanisms in the 1300s, 1400s, they thought they were innovating. They had no idea Greeks had done it 400 years earlier. The Islamic preservation. Islamic scholars, 800 and 1200 AD, preserved more Greek knowledge than Europeans. They translated Greek astronomical texts, built sophisticated astrolabes, developed mechanical clocks, advanced mathematical astronomy, but they apparently didn't know about the Antikythera mechanism either. No Arabic texts describe similar devices either. The knowledge was already lost when they began translating, or such devices were kept secret, guild knowledge, or examples existed but haven't been found. The Archimedes connection. Cicero, Roman writer, 106 to 43 BC, mentions Archimedes' sphere. Archimedes fastened on a globe the movements of moon, sun, and 5 wandering stars. When Gallus moved the globe, it was actually true that the moon succeeded the sun by as many revolutions on the bronze contrivance as in the sky itself. This sounds exactly like the Antikythera mechanism. Archimedes died in 212 BC. The Antikythera mechanism dates to around 100 BC. Possibly, Archimedes designed an early version. Later craftsmen refined the design. The tradition continued for a century or more. then disappeared when Rome conquered Greece. The tragic irony. Ancient Greeks had knowledge we lost for over 1,000 years. They could predict eclipses mechanically, calculate astronomical positions with geared computers, manufacture precision components medieval Europeans couldn't. The Renaissance rediscovered this knowledge only partially. Full understanding didn't return until the Industrial Revolution, when precision machining made complex clockwork possible again. Yet the question: what else did they know? What other devices existed? What knowledge burned with Alexandria? The Antikythera mechanism is probably not unique. It's just the only one we found. The Antikythera mechanism represents knowledge from multiple ancient traditions. It's not Greek in isolation, it's a synthesis. The Babylonian Foundation. Babylonian astronomers, around 700 to 300 BC, developed systematic observation of celestial phenomena, mathematical models of planetary motion, eclipse prediction cycles, Saros cycle, lunar and solar period calculations. The Babylonians were obsessive record keepers. For centuries, they tracked moon phases, planetary positions, eclipse occurrences, seasonal changes. From this data, they extracted patterns, cycles.predictive models. The Antikythera mechanism uses Babylonian cycles, particularly the 223-month Saros eclipse cycle, the Greek contribution. Greek astronomers and mathematicians refined Babylonian observations. Hipparchus, 190–120 BC, calculated the length of the solar year, discovered the precession of the equinoxes, measured lunar cycles with precision, created star catalogs. Archimedes, 287–212 BC, built mechanical devices described in texts but now lost. Developed geometric models of celestial motion. Possibly designed orreries, mechanical solar system models. The Greeks turned Babylonian observations into geometric models. They asked why, not just when. The mechanical tradition. The Greeks had a tradition of building mechanical devices. Ctesibius, 285–222 BC, invented the water clock, created pneumatic devices, pioneered mechanical automation. Philo of Byzantium, 280–220 BC, wrote treatises on mechanics, described automata and machines. Archimedes, again. Ancient sources mention his sphere that showed planetary motion, possibly a mechanical device similar to the Antikythera mechanism. This wasn't an isolated invention. It came from a tradition. The missing link. Here's the problem. We have Babylonian astronomical data, Greek mathematical theory, Greek mechanical engineering tradition, the Antikythera mechanism itself, but we don't have detailed treatises explaining how to build such mechanisms, other surviving examples of similar devices, clear documentation of the knowledge transfer. The knowledge clearly existed. The mechanism proves it, but the texts explaining it are gone. The Antikythera mechanism represents knowledge from multiple ancient traditions. It's not Greek in isolation. It's a synthesis. The Babylonian Foundation. Babylonian astronomers, around 700 to 300 BC, developed systematic observation of celestial phenomena, mathematical models of planetary motion, eclipse prediction cycles, Saros cycle, lunar and solar period calculations. The Babylonians were obsessive record keepers. For centuries, they tracked moon phases, planetary positions, eclipse occurrences, seasonal changes. From this data, they extracted patterns, cycles.predictive models. The Antikythera mechanism uses Babylonian cycles, particularly the 223-month Saros eclipse cycle, the Greek contribution. Greek astronomers and mathematicians refined Babylonian observations. Hipparchus, 190–120 BC, calculated the length of the solar year, discovered the precession of the equinoxes, measured lunar cycles with precision, created star catalogs. Archimedes, 287–212 BC, built mechanical devices described in texts but now lost, developed geometric models of celestial motion, possibly designed orreries, mechanical solar system models. The Greeks turned Babylonian observations into geometric models. They asked why, not just when. The mechanical tradition. The Greeks had a tradition of building mechanical devices. Ctesibius, 285–202 BC, invented the water clock, created pneumatic devices, pioneered mechanical automation. Philo of Byzantium, 280–220 BC, wrote treatises on mechanics, described automata and machines. Archimedes, again, ancient sources mention his sphere that showed planetary motion, possibly a mechanical device similar to the Antikythera Mechanism. This wasn't an isolated invention. It came from a tradition. The missing link. Here's the problem. We have Babylonian astronomical data, Greek mathematical theory, Greek mechanical engineering tradition, the Antikythera mechanism itself, but we don't have detailed treatises explaining how to build such mechanisms, other surviving examples of similar devices, clear documentation of the knowledge transfer. The knowledge clearly existed. The mechanism proves it, but the texts explaining it are gone. The Antikythera mechanism is unique. In 120-plus years of archaeology across the Mediterranean and Near East, no other example has been found. No similar devices, no partial mechanisms, no comparable geared computers, just this one, from one shipwreck. Why? The preservation problem. Bronze corrodes. Wood rots, complex mechanisms disintegrate. The Antikythera mechanism survived only because it sank in seawater quickly, sealed from air. It was buried in sediment, protected from currents. It was found before complete disintegration. Even so, its badly corroded and incomplete land-based examples would have corroded completely, been melted down for scrap metal. The melting factor. Bronze was valuable, reusable. When devices broke or became obsolete, they were melted down. The metal was recast into new objects. No trace remained. The Antikythera mechanism survived only because it sank before anyone could recycle it. The statistical argument. One shipwreck, one mechanism. If one random shipwreck contained an Antikythera-type device, probability suggests many others existed. The production question. Was the Antikythera mechanism a one-off experiment or a manufactured product? Evidence suggests manufacturing. The inscriptions are like a user manual. The precision suggests refined production techniques. The complexity suggests institutional support. This wasn't a unique prototype. It was likely one of several, or many. The Guild secret theory. One possibility: the knowledge was proprietary. Craftsmen kept techniques secret. They didn't write public manuals. When the Guild tradition broke, the knowledge died. The Roman conquest effect. Romans didn't value theoretical science or complex astronomical devices enough to preserve them. Funding dried up, workshops closed. The tradition faded. The archaeological blind spot. How many Antikythera-type mechanisms have been found and misidentified, stored in museum basements uncatalogued? We found Antikythera only by accident. The lost siblings. Somewhere in the Mediterranean. Ships carrying similar mechanisms sank, or they sit in silt, waiting, somewhere on land. Mechanisms were built, used, then recycled. Knowledge was transmitted, then lost. The Antikythera mechanism is an orphan. Its siblings, if they existed, are gone. The Antikythera mechanism proves something unsettling. Ancient civilizations had capabilities we didn't know about. They built sophisticated devices that left almost no trace. What else did they achieve that vanished completely? The technology ceiling. Question. We assume technological progress is linear. Simple, complex, primitive, advanced, ancient, modern, but the Antikythera mechanism breaks this model. It shows ancient Greeks achieved complexity we thought impossible for their era. Technology was lost and had to be rediscovered. Progress is not guaranteed. Knowledge can regress. If they built this, what else did they build? The automata evidence. Ancient sources describe mechanical automata. Philo of Byzantium, 280–220 BC, described mechanical birds that chirped. Automated theater devices, self-operating mechanisms. Hero of Alexandria, 1070 AD. Vending machine for holy water. Automatic temple doors. Steam-powered rotating sphere, Aeola Pili. Programmable cart using pegs and strings. If they could build these, they had geared mechanisms, pneumatic systems, hydraulic engineering, programmable sequences, the lost architectural technology. How did Romans make concrete that's still standing after 2,000 years? Modern concrete degrades in decades. Roman concrete improves with age. The recipe was lost, only recently partially reconstructed. If we lost concrete, a fundamental building material, what else did we lose? The Antikythera class. The mechanism suggests a category of lost technology. Antikythera class devices, sophisticated mechanical systems, limited production, perishable materials, bronze, wood, knowledge concentrated in small groups, lost when social systems collapsed. How many other Antikythera class devices existed? Astronomical calculators, mechanical computing devices, precision instruments, automated systems, all gone, all forgotten. The Baghdad Battery. An archaeological artifact, a clay jar with copper and iron components. Some researchers propose it's an ancient battery, 250 BC, 640 AD. If it is a battery, that suggests understanding of electrochemistry, practical applications, electroplating, another lost technology. The Antikythera mechanism was recovered in 1901, but we didn't understand what it did until the 2000s, 100 years of study, and we still needed 21st century technology to crack the code. The initial confusion, 1901–1950s. Early researchers saw corroded bronze fragments, gear teeth, Greek inscriptions. They proposed theories, navigation instrument, astrolabe, clock, but none made sense with the data. The mechanism was too complex for proposed functions, too sophisticated for its time. The Derek de Sola Price breakthrough, 1951. Physicist Derek de Sola Price examined the mechanism using X-rays. He saw multiple gears inside, complex internal structure, sophisticated design. He realized this was an astronomical calculator. He wrote a groundbreaking paper proposing the mechanism predicted lunar cycles and eclipses. The scientific community was skeptical. Ancient Greeks couldn't do this, yet the evidence was undeniable. The limitations of analog imaging, 1950s, 1990s. X-rays showed gear structures, but the image was fuzzy, two-dimensional, and hard to interpret. Researchers could count gears and estimate tooth counts, but couldn't see detail clearly. The mechanism remained partially mysterious. The CT scan revolution, 2005–2007. In 2005, researchers used high-resolution CT, computed tomography, scanning. For the first time, three-dimensional images of internal gears. Tooth count precisely determined. Inscriptions readable with new clarity. The data was revolutionary. The computer reconstruction, 2006. Using CT data, researchers built computer models of the mechanism, simulating how gears meshed and calculating its outputs. Computer simulation revealed how the differential gear worked, what astronomical cycles it calculated, what accuracy it achieved. The Inscription Translation, 2005-2015. High-resolution imaging revealed most of the 3,000-character Greek inscription. When translated, it provided instructions for use, descriptions of dials. The inscriptions were like an ancient user manual. The Precision Analysis. Modern tools allowed analysis of gear tooth spacing, tool mark patterns, and manufacturing techniques. For the first time, we could understand not just the device, but how it was made. The failed attempts to replicate. Researchers tried building working replicas using ancient tools. This proved ancient Greeks had the skill to build such devices. The remaining mysteries. Even with modern imaging, questions remain. Which gears represent which astronomical phenomena? How many similar devices existed? Who designed it? Some gears remain too corroded to analyze fully. What's strange? We understand the mechanism's function better than we understand how it was designed. We can see what it does, but we can't trace the conceptual steps that led to its design. How did someone first imagine? Using gears to model astronomical cycles, calculating precise tooth counts for accuracy, integrating complex multiple functions. The evolutionary pathway is missing. Modern science needed. CT scanners, 3D imaging software, high-resolution cameras. To understand a device made with bronze, files, chisels, basic measuring tools. Ancient craftsmen needed less technology, but more knowledge. We have more technology, but struggled to understand their knowledge. If it took us 100+ years and 21st century technology to understand a 2,000-year-old device, how much other ancient knowledge are we missing? What other mechanisms are sitting in museums unrecognized? What else did they build that we're still too blind to see? Our knowledge is less protected. We should be creating redundant copies in multiple formats, encoding knowledge in durable materials, not just digital, documenting how to access and use it, not assuming future people will know, preserving in multiple locations, not relying on centralized archives. We're not doing this, we're centralizing, digitizing, depending on systems. The humility requirement. The Antikythera Mechanism teaches humility. It says, you're not immune to knowledge loss. Sophistication doesn't guarantee survival. Your technology might be lost. Your achievements might be forgotten. In 2,000 years, scholars might argue about whether you really existed. The appropriate response is, preserve knowledge deliberately. Create backups of backups. Document in simple, durable formats. Don't assume your systems will last. Build for the possibility of collapse. We're doing the opposite. Our knowledge is less protected. We should be creating redundant copies in multiple formats, encoding knowledge in durable materials, not just digital, documenting how to access and use it, not assuming future people will know, preserving in multiple locations, not relying on centralized archives. We're not doing this, we're centralizing, digitizing, depending on systems. The humility requirement. The Antikythera Mechanism teaches humility. It says, you're not immune to knowledge loss. Sophistication doesn't guarantee survival. Your technology might be lost. Your achievements might be forgotten. In 2,000 years, scholars might argue about whether you really existed. The appropriate response is, preserve knowledge deliberately. Create backups of backups. Document in simple, durable formats. Don't assume your systems will last. Build for the possibility of collapse. We're doing the opposite.